Okay? Now, since today's lesson is a review, I'm going to be going through like a lot in one thing, but it's all stuff that we've probably seen before, so just slow me down if you need to. Like, be like, wait, I don't remember this. Can you re-explain that, whatever. Otherwise, I'm going to be kind of jumping around, okay? Now, for your warm-up, in each of these situations, it says solve for x, right? So solving for x is finding an x value that makes it true, right? So something I can plug in here, and it would be 3 squared plus that squared equals 5 squared. Now, in my last class, somebody said, well, if everything's being squared, then this 3 plus that should equal 5. I should just be able to say that is 2. 3 plus 2 equals 5, right?
So that's not how that works.
Not quite how that works, okay? We do want to actually do the math to figure this out, okay? So, it's a good thought, but it doesn't work that way. Now, if I'm trying to get x by itself, right? Well, I can't because it's being squared. It's being raised to a power. So I'll just get that power by itself first, right? In order to do that, I kind of need to evaluate some stuff here. 3 squared is what? 9. So let me get this in an easier format. And 5 squared is 25. This is a little easier to get by itself. Now I'm not dealing with any exponents except for with my x. Now I would get x squared by itself by minus 9 on both sides. I'd have x squared equals 16. Okay? X squared equals 16. Square root. I get x equals what? Plus or minus 4. Why? Why plus or minus right now? Right, because we're looking for solutions. I know, it's confusing. We use plus or minus sometimes we don't. Think, am I solving? Am I solving right now? Am I finding a solution? Am I finding something that makes it true? Because if I am, I need to find all the things that make it true. And negative 4 squared, if I plugged it in, would make this true. Okay? So you would need to account for that. Later on today, we won't use it. And we'll talk about why we won't use it, right? You have to be like thinking about the situation. Is this a plus or minus situation, or is it not? All right, next one's pretty similar, right? Just kind of rearranged a little. X squared plus 64 equals 100. Subtract 64. I get x squared equals 36, right? If I square root this and I square root that, I get x equals what? Plus or minus 6. Because both 6 and negative 6 make this true. Okay, moving along. This next one, okay, so x squared plus x squared equals 8 squared. So it's like, okay, if I'm supposed to get x by itself, do I just square root the whole thing right now? Yes, exactly. We haven't talked about this in a while, but you always simplify before you solve, right? Like if I had x plus 2x plus 2x equals 5, I wouldn't start trying to figure out what x is until I did what? And combine all these like terms. That's 5x equals 5. Oh, okay, now I divide each side by 5, right? You bring it all together first if you can. Combine your like terms. And these are like terms, x squared and x squared. That would be 2x squared, right? 2x squared equals 64. Now, I saw this a lot in the test. Divide by 2. You're not isolated yet. Can't square root right now. It's not, the power is being raised on the x. So I divide by 2, I get x squared equals 32. Now what? Square root. Yeah, it doesn't have to be a perfect square to square root. And I get x equals plus or minus the square root of 32. But I did a plus or minus even though I didn't get anything out of it. Why? Well, yes, we're not even done. We need to simplify. But why did I do a plus or minus even though I didn't pull out of the square root? Because negative square root of 32, if I plugged it in, would make this true. and positive square root of 32 if I plugged it in would make this true, right? Now, okay, you're right that we're not simplified. We would jailbreak this or break it down. If I break it down, I see that it's 16 times 2, right? So square root of 16 is 4. So this is x equals plus or minus 4 square root of 2, right? Or you could jailbreak that all the way down. You'd find a pair and another pair, and then they would come out, okay? But we've kind of hit that a lot, so I'm going to move on. All right, this one, we're already isolated. Great, we just need to figure out what this side is. 25 plus 100 equals x squared. 125 equals x squared. Square root, x equals plus or minus 5 radical 5. Yep. Square root of 125 breaks down to that. Okay? Now, what do you think this reminds you from geometry? The Pythagorean Theorem, right? You're going to need to be doing this kind of algebra when you're solving triangles, right? Something squared plus something squared equals something squared. If that doesn't sound familiar, we're getting there. Question?
So, like, what if you use the formula for Pythagoras, like a squared plus b squared?
Yeah, so we're going to talk about that today. Yeah. Okay, before we do, let's talk about triangles in general. I'm going to start from the basics here. Triangles have, what was that? 3 sides. What else?
They equal 180, like
The angles. So how many angles? 3 angles. And we use this little, looks like a little mini angle to represent angle. By the way, we use a little tiny triangle to represent triangle, right? And the angles add to 180 degrees. And we put a little tiny little circle to show degrees, right? Sounding familiar? Okay, triangle names. For example, you might have triangle ABC. Say again? Oh, we'll talk about types in a second, but just like how you name a triangle. If you have a triangle ABC, that is a triangle with angles A, B, and C, right? You name it with the angles, right? If you had an angle, let's say I'm talking about angle B right now. I could say angle B, or I could say angle ABC, where the letter in the middle is what matters, right? Why would we need 3? Well, what if I had this situation? A, B, C, and D. And I just said angle B. You'd be like, well, which one, right? But then what if I said angle DBC? Well, now you would trace it. You'd be like DBC. I must mean this one, right? So you need 3 letters sometimes to zero in on what that angle is, okay? All right, let's talk about the types. What do these little dashes mean?
Congruency marks.
Congruency. So let's talk about congruency. Congruent means same. Same / equal if it's an amount, but it could just mean same size, same shape, like it means a lot of things in geometry. Same / equal, and if you have the same amount of dashes, that is somebody telling you, somebody who made the diagram, that those are congruent, right? So if I all have the same dashes, what does that mean about the sides here? They're all equal, and we call that equilateral. Now, the word lateral means to move side to side. That's how you remember it. That one means equal sides, right? Equilateral would be 3 congruent sides. And I just used the symbol for congruent, which is an equal sign with a squiggly on top. Okay? Now, this next one does not have 3 equal sides or congruent sides. It has, all I see here is all you can go with is what is given. What is given here? 2 equal sides, 2 congruent sides. What is that called? Anybody remember? Isosceles. Good. Now, this is a great example of how, this is an isosceles triangle, of how geometry goes sometimes. They give you some information. You infer more information. You know, hey, if I have 2 equal sides, I also have 2 equal angles, and you add that to the diagram, right? So a lot of times they give you stuff, and then you add stuff, right? You say, well, I know because that is true, this is true. So I also have 2 congruent angles, okay? How about this one? It's got nothing. Scalene meaning what? Yeah, there's no congruency here. Scalene triangle is no congruent sides. That's a great point you're making. It almost looks like a right angle.
But it's like maybe 8 instead of
But even if this looked like this, you couldn't assume it was a right angle. Why not? It's only a right angle if they tell you, hey, that is a right angle right there. Okay? You can never assume. What if it's 89.9 degrees, right? Okay, so if that was equilateral, then this is equiangular. And what do you notice about this diagram? 3 congruent angles and 3 congruent sides. In fact, all they had to do in this one is give you the angles, and you would know by your definitions that is also 3 equal sides. Okay, now, what about this one? What do you notice about this one? Not necessarily. Sometimes you need the dash. Like if it had a dash, I see why you're thinking that. That's actually probably a flaw. What's that? Well, I'm not. That's not what the point of this triangle is. It's an acute triangle, right? We can tell what about this? That all the angles are what? All angles are less than 90 degrees. How do you know? They're closed more than the 90-degree angle, right? Speaking of a 90-degree angle, how do you know when you have one? They have to give you the box. Okay, and so that's a right triangle, right? And that's what we'll be focused on mostly. And it's got one 90-degree angle. Now, what do you call a triangle with 2 90-degree angles? Not a triangle, because that's already 180 degrees, and you're added degrees for your third angle, right? Question, Kayla?
What's the spelling for the first name?
Oh, man, I put 2 Q's. Thank you. It's equiangular. And I put 2 Q's. Question in the back. All the angles are less than 90 degrees, yes. And you can remember that one versus the next one because they're all little cute little angles. They're just a little cute. They're little cute, tiny little angles. All right, this one is obtuse. If you ever want to, I don't suggest you insult anyone ever. But if you ever want to be really sophisticated, just be like, why are you being so obtuse? And they'll be like, what? What are you talking about? So, one angle over 90 degrees. And you can tell because it's opened up more than that square, right? It opens up more. That's what an angle does. It's how much are we opening up. Okay. All right, so we're going to lock in on one type of triangle. This type of triangle, which is? A right triangle. And right triangles are special. They have special relationships we can use, okay? Let's start with, before we get into it, this symbol right here, which is called?
Theta.
Yes, it is. Nice. Y'all know your stuff. Okay, and what does theta represent?
It's the angle.
What angle?
The angle of the given section. Like, let's say if the missing.
The missing angle. This is a missing piece. This is a missing angle. And it's okay. You knew the name. Missing angle. So this is kind of like x. It's our go-to for unknowns, but for geometry. Now, there's still x's in geometry for like a missing side or something. But if we're going for missing angle, we use theta. Right?
Please don't make me use theta.
I'm sorry, theta will be used this week. Okay? All right. So now let's talk about these different parts, right? Let's start with the most fun one to say, which is the
Obtuse.
obtuse is a fun angle. I'm talking about the sides here.
Oh, are you talking about
The hypotenuse, the hippopotamus. Hypotenuse. Now, how on earth could I know this was the hypotenuse?
It's
I hear two things, and I agree with the both. Sometimes you need both of them, though. Yeah.
It's opposite from the right angle.
Right. So it is opposite the 90-degree angle, right? So a couple things here. It's opposite the 90-degree angle. Now, something else was said that is true. What is that? It's the longest side. But sometimes it's not very clear what the longest side is. So then you just look, because what if they're like so close, right? So you look, what's opposite the 90-degree angle? Okay, now, what do we call these other pieces? This one and this one.
There's opposite and adjacent.
Not yet. Can't talk about that unless I have a theta.
Oh, dang it.
Well, we're going there. If this is the hypotenuse, these are the
A and B.
words. Give me the words. The legs. These are the legs, right? And I heard words like adjacent and opposite, and of course those are going to come into play, but that can't come into play unless we have a theta. And now I have a theta. Now I can talk about opposite and adjacent, because opposite and adjacent is relative to where theta is. Where is your unknown, or even your known? And then you say, okay, well, what's my opposite leg and what's my adjacent leg? So in this case, where's my opposite?
The below. To the left.
The one that is not touching it, right? So this is my opposite leg. And adjacent, it's touching, right? It's on, right? Adjacent means next to, right? So this is my adjacent leg. Right? And that's going to be super important when we're getting into opposite divided by adjacent. Like, you need to be able to identify which is which, right? So this is my theta, that's my adjacent, that's my opposite. Okay? Now, I heard some letters as well. Well, before we get there, what letters do we associate with these sides? A, B, and C. Do I just put them anywhere I want?
No. No. A is adjacent.
C is the hypotenuse.
Because that's how
And then we have A, and we have B. Now, I heard somebody say A is shortest, B is the second shortest. Can you tell a lot of the time?
No.
It doesn't really matter. They're both on the same side of the equation. Make one A and make one B. Yeah.
But C
Don't we
has
have
to
to
always
put the numbers like on each side, like corners, or not? Just
Well, we don't know anything about this triangle. We're just naming it right now.
usually when you like wanna put it A, B, C, it's like on each point, like side, but here it's not.
Yeah, I moved it over because I had words there already. You'll see in the next one.
Like A, I mean like A on the 90, B on top, and C on top.
Oh, so you're talking about angles names. So lowercase for side lengths, and then angle angles, we might say, in fact, we would say, this is my A angle, this is my B angle, and this is my C angle. Something like that, you're saying?
Yeah.
Yeah, that would be naming the angles. We were naming the sides. But good point. We might want to add that.
The angles, we can name them. It has to
So,
be C here and A.
well, yeah, if that's side A, this could be angle A because it's shining upon it. Okay. All right. Let's. I'm gonna skip the whole point of this. Why is all this stuff valuable? Well, there's this guy. His name was Pythagoras. Pythagorean. He came up with a theorem. He said, guys, I figured something out. If you take one of the legs and you square it, and you take another one of the legs and you square it, and it's a right triangle, it's equal to the hypotenuse length squared. Is this true for all triangles? No. Just right triangles. Okay, why is this valuable? Well, anytime we know a relationship in math, it's valuable because when there's a missing piece of that relationship, we can solve for the other piece of that relationship, right? For instance, we write any of this down? Are we good? Okay, this situation. Well, can I use Pythagorean Theorem here? Who says I can use this? Not yet.
It's not a 90 degree.
I don't know if this is a right triangle. Good. I wanted you to catch that. All right, now pretend it had that. Now can I use this? Yeah. Okay, so now I know it's a right triangle. I know that a squared plus b squared equals c squared. So I have to decide where's my a, where's my b, where's my c. Well, easy place to start is what? Hypotenuse, because it's always across, right? So this is my c. So c equals 8, right? Where should my a go? A equals 4, so that means b equals x. I know what each thing is. I plug in each thing, right? So that means 4 squared plus x squared equals 8 squared. Does that look familiar from your warm-up? Pretty similar, right? So this becomes 16 plus x squared equals 64. Subtract 16. Subtract 16. X squared equals 48, right? Square root, square root. I get x equals, and then I have the square root of what? What is 48 reduced to? Anybody know? Or do you need some time?
6 times 8.
16 and 3. So, yeah, so 4 square root of 3. And you don't need to do that in your head if you still need to jailbreak that down. Now, question. Great question. I'm glad you asked. Was I solving an equation? I was, but it was for a point. Yeah. Exactly. What was my original goal? To find a length of a triangle, right? The equation is something I made that I was trying to use to set it up, right? So just because it makes my equation true doesn't mean it makes the original question true. The original question asked for a length, and I can't have negative length. You can't have negative 5 centimeters, right? So positive only. So if you want to write yourself a note, no plus or minus for length. Okay, so that's one type of problem, right, that you could have with a missing piece. But you could also have missing angles, right? And you don't need a right triangle for this. This brings up the triangle sum theorem.
Isn't that like 180 minus 68 minus 37?
It sure is. Yeah, so the triangle sum theorem says basically in triangle ABC, angle A plus angle B plus angle C must equal 180 degrees, right? If you have three angles, they add up to 180. We talked about that. But when you put it into a formula like that, it makes it pretty helpful to find missing pieces, right? Like, for instance, here, well, if I know this, this, and this add up to 180, I set up an equation that says x plus 68 plus 47 equals 180 degrees. And I just solve for my x. Bring those two numbers together, subtract them from 180, and I get x equals, I'm not going to actually do that, right? We know what to do there, right? Add these together, subtract them from 180, 65 degrees. So I found my missing piece. If I need to check my work, add them all up, they better be 180. Right? Now, it gets a little more complicated when you have expressions and not numbers, but it's still the same concept. This, all together must be 180. So I say, okay, x plus 10 plus 2x plus 20 plus 2x minus 5 equals 180. Again, just like in our warm-up, would I try to find x before I simplify this? No. I'm going to bring as much together, simplify, then solve, right? Find those like terms. X, 2x, that's 5x. 10, 20 minus 5 plus 25 equals 180. Solve for x. Minus 25, divide by 5. 5x equals 55. Divide by 5, divide by 5. X equals 31. Wow, perfect. I was trying to find all the missing angles of this triangle. I just found them. No, I didn't find them, right? Biggest mistake here is to do all the right math but not answer the question. If I said, find the missing angles in this triangle, have you found any of them yet? No, you just found a piece of them. If x is 31 and this angle is x plus 10, what's the actual angle? 41. Right? You don't always have to do it in your head, but that's the concept, right? 2x plus 20, well, that's 62 plus 20, that's 82, right? And then this one, you either subtract these two from 180 or keep plugging in. 62 minus 5 is 57. Check your work by adding them all up. They must be 180. Okay, one last thing we got to cover that's going to come up in this unit is proportions. What is a proportion? What is a proportion? And the hint is there are two written right below. That is an example of
Something out of something.
Say again? A fraction equaling a fraction. So a fraction equal to a fraction, but there's more to it than that. In fact, we would like to think of it as a ratio equal to a ratio, because ratios are what? Like a ratio shows you a what? Proportion, sure.
A fraction of something.
Okay, the ratio of male to female students is 5 to 3. What does that tell you?
That's a fraction.
But it's a comparison. It's a relationship, right? If you then told me the total number of male students, I could find the total number of female students by knowing the ratio, right? So a ratio and a proportion shows a relationship. So let's go with that example. 3 to 5 is the male to female proportion at a school, right? And then I tell you, well, actually, I just counted all the males. And it turns out there are 300 males. Could you tell me how many females there are? How many? 500. Why? Because 300 500ths equals 3/5. That's the relationship. That's the ratio. That's the proportion. Okay. Now there are missing pieces that are, it's not always that easy to figure out the missing piece of a proportion, right? So we have a strategy. We have a thing we do every single time. To solve, and this is the last piece, anybody remember? So to solve, cross multiply. So in its current form, this is really hard to figure out what x is, right? But there's a rule with proportions that says this times this will equal this times this, so you can make a new equation, and that will be easier to solve. 2 times 7x will equal 3 times what? X minus 9 in its entirety. That's a big mistake that's made, right? Not put parentheses around that x minus 9. That'll change your answer here. So that's 14x equals 3x minus 27, and you solve from there. This isn't like the cleanest problem. Wait, no, I wouldn't move the 27. Minus 3x minus 3x. 11x equals negative 27. Divide by 11. Divide by 11. X equals negative 27 elevenths. Okay? One more, and then I'll hand out your homework. Cross product, right? 8 times 7 is 56. X times 2x is 2x squared. Right? And then this is similar to our warm-up, right? Divide by 2, divide by 2. X squared equals 28. Square root, square root. I get x equals plus or minus. Very good. Why? We're solving, right? We're solving. That's all, our only goal right now is to solve. So this would be 2 square root of 7. All right? And again, if you don't know how I got to 2 square root of 7, that's a jailbreak situation. That's a breakdown situation. Just skipping that since we've done it so much. All right. You have over 10 minutes to do your homework. Knock it out.